Okay, so I'm going to talk to you about the dating problem, or Magdon's 1 over E theorem for dating. So dating. This is a classic online learning problem. Okay. The main difference with reinforcement learning is as you're making your decisions, you don't really experience reward. Okay, that comes at the end. Okay. So dating, and we're going to talk about Magdon's 1 over E theorem for dating. Okay, this is an example of what's called an online decision-making problem. Okay, and it has gone by various names: the secretary problem, the interviewing problem, and I'll give an application of this problem to a choice that you might be making very soon, those of you who are applying for jobs. Okay, so here's the setup. So there's you, okay, and waiting in line to date you are N people. And we won't worry about exactly where those N people came from or how you got into this position or whatever. So there are N people: person 1, person 2, person 3, up to person N. So there are N people waiting to date you. Okay, and let us assume that dating happens in the normal way. So if you meet someone, you date them, and you can establish and estimate right then and there what's their value to you. So there's some value V1, some value V2, some value V3, and some value Vn. Interesting. Okay, good. So you date a lot. Okay. So what's the game? What's the deal here? Okay. So what's the deal here is, at the end of the day, you're going to have to stop this process. So this is an example of an optimal stopping problem. You're going to have to stop this process and say, you're the one. Let's get married. And then if they agree, boom, boom, boom. Okay, everything happens. Now we can assume that all the people here that I've listed are people who would agree. Okay. So the ones who wouldn't agree to sort of settle down with you, we've just thrown them out for the moment, okay, just to make things simple. Okay, so let's list the assumptions. The assumptions are, 1, these values, so the people arrive to you in some random order. So people arrive in a random order. Okay. You can evaluate each person as they arrive, when they arrive. Can evaluate each person. This means you can compute Vi at the time I. So imagine that at time step 1, whatever time step means, maybe a month, you date person 1. Then maybe for the next month, you date person 2. And at the time that you're dating them, you can evaluate them. Okay, so this is an assumption. Now, here's an interesting assumption, and it makes sense for dating. When you date person I, so when you date person I, at time I, so time is there, and it's an online decision-making problem. When you date person I, you must make a decision. So you must either accept or reject. Okay. So let's think about this in the context of dating. So if you accept, it means you settle down and whatever, you get married, and it would be highly unusual if you then continue dating. Okay. And if you reject, so you say bye-bye. Okay. And you move on to the next, and you date, and then at some point you come to the end, and you say, you know what? I really like that person. You go to them and say, you know what? I made a mistake rejecting you. Let's get married. You're probably going to get hammered. Okay. So, when you make the decision, accept or reject, it's final. Okay. And so that corresponds to one of our, requirements in the, or one of the sort of constraints in the reinforcement learning setup. You're making decisions and they have real consequences in real time. It's an online decision-making problem. Okay. There's a very well-defined arrow of time, and you cannot go backwards in time. Your decision is permanent. Okay. And the last and sort of most controversial assumption is, you want to succeed. And how do we define success? Success means you want to get the best person. Success means you get the best. Nothing else will do. And now let's think about this from the context of dating. let's say you've rejected, and then, you accept. Will you accept someone who's worse than who you've rejected? Probably not. You're going to be, sour grapes your whole life. Think, oh man, I'm stuck with this person, and look at that person who I rejected who's way better. So you'll never accept someone who's worse than people you have already seen. Okay, we may argue about the assumption, but okay, we're making an assumption. Okay. And then, supposing that this person is better than everyone you've seen, but not the best. And as life goes on, you meet people, and then finally, suddenly by accident, you meet the person who's the best, and you're looking at, who you're currently with. You're looking at the best. It's going to be an explosion. So it's reasonable to say that success occurs only when you get the best. Okay. Now, this problem and these assumptions more or less apply in many settings. For example, interviewing. You're interviewing people for a job. Okay. When you interview them, they come in a random order, and when you interview them, you can evaluate them. Okay. And then you have to make a decision. And if you accept, well, you've hired them. It's permanent. You can't go back on your decision. If you reject, they go and get another job. So you can't come back to them 3 months later and say, oh, you know what, I made a mistake, reject you. Oh, well, sorry, buddy, I've now got my job at Google. Okay? So you have to accept and reject right then and there. Okay. Now, in the case of interviewing, maybe it's not so bad if you don't get the best. But still, we are making this assumption. Let's talk about job offers. So you guys are going to be, getting job offers. Job offer 1, it's going to have a fuse, 1 week. Job offer 2, 1 week. Job offer 3, 1 week. So you're going to get the job offers, and they might come in a random order. You can evaluate each job offer. Okay. And if you accept, you're working there. If you reject, they're going to go and hire someone else. Okay. So this online decision-making problem is very common in practice. Job offers, interviewing, dating, and so on and so forth. Okay. So let's see whether we can analyze this in any sort of quantitative way and build a good strategy. Okay. So, how to optimally date? Optimal dating. Okay. So what can you do? Well, you can certainly do some strange things. You can accept the first person no matter what. You can just say, I'm going to blindly just date and make my decision randomly so that I accept a random person. Okay, so I'll pick ahead of time, I'm going to accept person number 12. And I pick 12 randomly. Okay, these are all crazy strategies. Let's try to think of a strategy that's reasonable. So a reasonable strategy is you have all your people. Okay, 1, 2, 3, 4, 5, who are going to be coming up to, let's say, K. Okay, and then here's N. Okay. And a reasonable strategy is to say, you know what, I have no idea what kind of values are available out there, so I need to learn, I need to explore a little. Okay. And so what I'm going to do is I'm going to set aside the first K. So I'm going to set aside the first K and explore / learn. What that means is that no matter how good someone is who pops up in here, you're not going to accept. Okay. You're just learning. You're trying to figure out what's going on out there in the world. Okay. And then after K, you're now ready to exploit. Exploit what? Exploit the knowledge you learn. So after K, if someone comes along at position I who beats everyone before, remember we're only after the best. So you're not going to be interested in a person who doesn't beat everyone before. So you care about people who beat everyone before. If someone comes along who beats everyone before, you accept. You're in the post-K phase. Okay? Okay. So that's the strategy. Now, what are the drawbacks? The drawbacks are, you might accept prematurely if this person beats everyone, but the best is yet to come. Okay, so you might accept prematurely. You might never accept if the best happens to be in this top K, in the first K that you just ignored. So there are chances of success and chances of failure. Okay? And we might think that, this problem is very, very daunting. Okay? Because I'm asked to choose the best, okay, and I'm seeing people in a random order, and we haven't said anything about N. N could be, in the case of dating, N might be 100, okay? Or in the case of interviewing, N might be 1,000. Or in the case of job offers, if you're lucky, N might be 1,000,000, okay? Okay. So what we're going to analyze is, okay, what are our chances of succeeding? What are our chances of picking the best? And let's analyze this strategy. Now, this strategy, it turns out, is the optimal form for a strategy. What else can you do? You learn and then you exploit. Okay. And let's ask the question, what are your chances of success? What's the probability of success? Okay. So let's see, when do you succeed? Okay. So you succeed, so assume K is fixed. You succeed providing that, okay, the person you pick, this guy is the best, because you're only after the best, and you didn't prematurely pick, okay? So among the I-1 people here, okay, among those people, the best must be in the first K. Because if the best among these I-1 is after K, then you will have prematurely picked that person, okay? And you won't pick I. Okay, so you succeed by picking I if the best is at I and you make it to I. You make it to I, which means that the best among the 1 to I-1 must be in the first K. That's when you succeed. You didn't pick prematurely, so you made it to I. So that means that the best among the first I-1 must be in the first K where you weren't allowed to pick. Okay? And then you made it to I, and then also I happens to be the best. So the best among the first I-1 is in the first K. That happens with probability K over I-1. And the chances that the best is at I is 1 over I. So by the law of total probability, this is the sum from I equals K plus 1, because you only start picking after K. So sum from I equals K plus 1 to N, 1 over N, that's the probability that the ith guy is the best, times the probability that you make it to I, times K over I-1, which is equal to K over N, the sum from I equals K plus 1 to N, of 1 over I-1. So this is basically the sum of 1 over I from K to N. So this is approximately equal to K over N log of N over K. Approximately. Okay, interesting. So this is basically log X over X, where X equals N over K. Okay, so we can optimize with respect to X, and I leave this as an exercise for you. Optimize with respect to X, that gives you that X is equal to E. Okay. So that means that N over K is optimized when N over K star is equal to E, or K star is equal to N over E. Okay. So let's see, what are your chances of success? And this is a baby miracle. What are your chances of success in this apparently very hard-looking online decision-making problem? Your chances of success are, so K over N. So K over N is 1 over E. So probability of success is, and actually it converges to K over N, which is, K over N is 1 over E. Log of N over K, but N over K is just E. So log of that is 1. So your probability of success is 1 over E. This is approximately equal to 40%. Rounding off and stuff like that. Wow! You could be picking among 1,000,000 alternatives, observing them sequentially one by one and evaluating and then saying accept or reject. Your chances of picking the one best, if you follow the optimal decision strategy, is approaching 40%. That's mind-blowing. I can pick the best among 1,000,000 alternatives, which I'm seeing sequentially one by one. Okay. And we're talking about success being you get the absolute best. Let's assume that the values are all different. Okay, so we don't have to deal with ties. Your chances of getting the absolute best are non-trivial, 40%. It's not zero. It's not a hopeless task. So there's hope to find the best mate. There is hope to find the best, whatever, secretary. There's hope to find, to pick, to accept the best job in this online process. Wow. Okay. Now, what's Magdon's 1 over E theorem for dating? So let's think about a typical person. Okay, maybe they start dating at age 15 and they stop dating at age 35. We don't need to go into too many details of how people behave. Let's just assume that they're dating at a uniform rate in whatever their period that they choose to date. So For some people, it may be a very high rate of dating. For some people, maybe a very low rate of dating. But as long as it's somewhat uniform, then this is 20 years. Okay, so K star is, n, however many that would be, which is proportional to 20 divided by E. So that's about 8 years. So, 20 years to about, so 20 divided by E is approximately 8. So 8. So 8 plus 15 is 23. So let's say 24, something like that. So around about 24. Okay. Well, I think 15 is a little bit optimistic. So let's say you're dating from like 20, seriously dating from like 20 to 40. Okay. 15-year-olds dating and possibly settling down and saying, yes, let's get married. Okay, that's crazy. Okay. But still, 20 years, and then 20 over E is about 8. So, 20 over E is about 8. So this is 28. Okay. So what does Magdon's 1 over E theorem say for dating? From the age of 20 to 28, you are exploring. Okay. After 28, you are ready to settle down. So I call this the pre-1 over E phase, and this is the post-1 over E phase. What does it mean, ready to settle down? You'll take anyone who comes along that beats everyone you've seen before. Now, there is a chance that with this strategy, you don't end up, finding someone. Okay. But the chances you find the best with this strategy are 40%. So, you can look and see in the US approximately what fraction of, people are remaining married. Okay. And this number is ballpark correct. Okay. You can ask, why is it folklore that people think, oh, you're too young to get married? That's what they're saying. You haven't hit the 1 over E phase yet. And roughly speaking, people have in their mind the age of something like 27, 28, which is where they're ready to settle down. They're no longer exploring the field, whatever that means. Somehow, it has biologically or socially evolved this number close to 28. And the notion of your pre-1 over E and post-1 over E. Okay, that was just for fun. And you can certainly do more precise analyses, and you can certainly relax the analysis that maybe the most fragile assumption is that the only thing you care about is the best. So you can do more sophisticated analysis, but the ballpark is always going to be something like this. Okay. A more important point, the message, okay, and this is where we're going to end. The message is that whenever you need to make decisions, okay, that involve data, that's learning from data. Here we're learning from data. Whenever you need to make decisions that involve data, you can use mathematics, you can use probability, you can use machine learning. You can quantitatively approach those problems. Checking out.